So we've discussed the formed elements of the blood, and now it's time to take a look at the liquid portion of blood, the plasma. Blood plasma is a clear yellowish liquid. It's yellow because it has a large abundance of proteins in it, and the proteins give it that yellowish color. It's the extracellular fluid of blood. 92%, give or take, is water, and the rest is a mixture of proteins and inorganic biochemicals. The function of plasma, of course, is to thin the blood enough that it can pass through blood vessels, and along the way we carry a lot of nutrients, gases, vitamins, hormones, wastes that are all dissolved in the plasma themselves or itself. And so it is the carrier component for much of what is transported around in blood. And because there is good communication between the peripheral tissues and the blood plasma, it regulates the fluid and electrolyte balances in those tissues and maintains body pH, or pH of the body fluids. So the plasma proteins are by far, after we talk about water, 92%, the remaining 8% is by far mostly plasma proteins. And these proteins are not nutrient proteins. Okay, so the nutrient proteins that are being transported in the blood are actually proteins that have been digested down to their individual amino acids. So we're not carrying nutrient proteins in the blood. It's just the proteins that are being made by the liver and then being dumped into the blood by the liver. So these proteins, their function is all about remaining in the blood, not about being absorbed into the extracellular fluids to be used as nutrients there. There are three groupings of plasma proteins: the albumins, the globulins, and fibrinogen, which is a specific type of protein. So albumins, globulins, and fibrinogen. And we're going to start by looking at the albumins. Albumins are more than half of the proteins, about 60% of the plasma proteins are albumin type, and they are the smallest of the plasma proteins. They're the shortest amino acid chains. And they're built in the liver and then sent from the liver fluids into blood. And they provide what is referred to as the colloid osmotic pressure of blood. So they provide the osmotic pressure that calls fluid into the blood. That's their biggest function. They can't leave the blood vessels. So when we get down to the capillaries, and I know we haven't talked about capillaries yet, that's next chapter, but when we get down to the capillaries, part of the function of the capillaries is to leak fluids out into the tissues, but after the fluids leak out, then at the far end of a capillary network, the fluids are drawn back in, and it's the colloid osmotic pressure of blood provided by the albumins that does this for us. They also have a transport function. They can grab a hold of things that will not dissolve easily in blood. Fatty acids, because they are nonpolar, do not interact well with water. So you can check back on chapter 2 to look at what a fatty acid looks like and to rediscover the conversation about polar versus nonpolar molecules. So anything that doesn't dissolve well in water, and those are the fats primarily. So steroid hormones don't dissolve in water, and some pigments like bilirubin don't actually it's bilirubin is attached to a transport protein, so it winds up at a very specific place. The same with iron. It's attached to a transport protein so that it can be picked up at the in the red bone marrow, so that we can recycle it into red blood cells. So, and some drugs may also require a transport protein to be moved around in the blood. The globulins, they're the next most abundant of the blood proteins, are primarily produced in the liver. Alpha and beta globulins are produced there, and they serve as transport proteins. But gamma globulins, these are that's the kind of official term for what an antibody is. It's a gamma globulin. They're produced by cells of the lymphatic system, and they're involved in immunity. And so here we have kind of a cartoon of what a gamma globulin looks like. We're going to come back around to gamma globulins when we get to the immune system. And then the least abundant of the blood proteins is fibrinogen. It's only about 4% of all the plasma proteins, also produced in the liver, and it is involved in blood coagulation. So the process of coagulation is the conversion of soluble, so dissolved in the plasma, fibrinogen, into insoluble strands of protein that are called fibrin. So we have to convert fibrinogen, which is soluble, into fibrin, which is insoluble and a strandy kind of protein. So proteins aren't the only thing carried in blood. Gases are carried in blood. Oxygen and carbon dioxide is dissolved in blood plasma. Nitrogen gas into, I should have said that, not just in, not free nitrogen, but nitrogen gas is also transported in blood plasma. But there's no physiological function for nitrogen gas. It just happens to be there. We can't use it for anything at all. So gases are transported in blood plasma as well as inside red blood cells. We've talked about that already. But they can dissolve in the plasma, and so it's an important transport mechanism as well as red blood cells. Nutrients are carried in blood as well. So the digested amino acids, they're all sent to the liver, and they're used there to make the plasma proteins, or they may be transported around to the cells, where the cells will use them to to build proteins as well. The simple sugars, mono and disaccharides. So a disaccharide is two simple sugars attached to each other. Glucose is a monosaccharide, but something like maltose is a disaccharide, so is sucrose is a disaccharide. But most of the simple sugars that we transport are monosaccharides like glucose. And then lipids, because they aren't soluble in blood, can be transported, but they have to be attached to transport proteins. And frequently they're like wrapped up in a little protein shell. And we call these packages of lipid wrapped up with transport protein shells lipoprotein complexes. And we'll look at that. We'll look at all of these when we get to digestive system. And actually it's really in the chapter right after the digestive system when we talk about nutrition. So we'll look a little bit at that. We also carry non-protein nitrogenous substances. So amino acids and proteins all have nitrogen in them, so they're nitrogenous substances as well. But when we metabolize amino acids, we produce waste materials that have nitrogen in them as well. So amino acids are carried in the blood. We've already talked about that. But nitrogenous wastes, the end products of amino acid and nucleic acid metabolism, are also produced. And they include things like urea, uric acid, and creatine. So these are all waste materials to the body and will be carried in the blood and transported eventually to the kidney so that they can be filtered out of the blood and removed from the body. And so if there's an increase in blood urea nitrogen, so that's the nitrogen in the form of urea, which is the primary waste product, then that can indicate kidney disorder or possibly the excessive metabolism of proteins. So people who are on starvation diets may wind up using proteins as an energy source, and that's going to produce higher levels of blood urea nitrogen. Last of all, electrolytes are carried in the blood. Electrolytes if you recall, hopefully from first semester, these are ions like sodium ion or the chloride ion, calcium ion. So electrolytes like these, potassium is another very important one. But then there are other ones that are useful at smaller levels like magnesium and iron. Okay, so all of these are ions. They are atoms that have lost or gained an electron. So sodium, for instance, has lost an electron. The chloride ion has gained an electron. So these are all, electrolytes are all absorbed by the intestine from digested foods, but they may also be byproducts of metabolic reactions. So HCO3 minus, that's the bicarbonate ion, is a byproduct of metabolic reactions. The most abundant plasma electrolytes in blood or in blood plasma are sodium and the chloride ion. And again, this bicarbonate ion is very important for maintaining plasma and body fluid pH, as well as it has a role, because it's so abundant, it has a role in maintaining osmotic pressure of blood too. Okay, so there you have it. Lots and lots of stuff in blood plasma. We will be looking at the nutritional aspects. When we get to nutrition, we'll be looking at the waste materials when we start talking about kidney function. Yeah, so lots and lots of opportunities still coming to learn more about these things.